Space is not the silent void we imagine. It crackles with whispers and screams we are only beginning to hear. For decades, scientists have pointed their antennas to the stars and captured signals that defy all explanation, bursts of energy and patterns of light with no known source. These are not messages we can understand, but cosmic mysteries that shake the foundations of physics itself. Today, we embark on a journey through 25 of the most baffling signals ever detected from the deep cosmos. By the end, you'll grasp just how strange, dynamic, and utterly unknown our universe truly is. We will encounter a single blast so powerful it was scribbled "wow," and rhythmic pulses once thought to be alien greetings. What force can hurl a millisecond of energy across billions of light years? What could possibly cause a star to dim in such impossible ways? The answers, if they exist, are waiting in the data. Are you ready to question everything you thought was out there? Our journey begins not with a whisper, but with a cosmic shout. On a quiet Ohio night in August of 1977, the Big Ear radio telescope was performing its routine scan of the heavens, a patient listener in the dark. Suddenly, its pen recorder spiked, tracing a signal so intense and so perfectly aligned with what scientists were looking for that it defied any simple explanation. The data printed out on a simple sheet of paper, a sequence of letters and numbers that would become legendary. It read 6EQUJ5. For 72 glorious seconds, this narrowband radio blast, billions of times stronger than the background noise of space, poured in from the direction of the constellation Sagittarius. It hit one precise frequency, a channel where cosmic static is naturally quiet, the very band a civilization might choose to send a deliberate hello across the stars. And then, just as suddenly as it arrived, it vanished. The astronomer on duty, Jerry Amon, circled the alphanumeric code on the printout and wrote a single, emphatic word beside it in red ink. Wow, that one word gave the signal its immortal name. In the decades since, every attempt to find it again has failed utterly. No telescope, no project, no dedicated search has ever heard that specific shout from that specific patch of sky. This absence is what makes the wow signal so profoundly haunting. It was not a repeating pulsar, not a natural stellar flare. It was a one-time event, a perfect candidate for an artificial beacon that simply stopped. Was it a fleeting message we missed, a cosmic accident we misinterpreted? Or was it, for one brief moment, a deliberate signal aimed right at us, only to be swallowed again by the eternal silence? Its mystery is absolute, a solitary question mark written in the static of the universe. While the wow signal was a singular enigma, a new class of cosmic outburst would soon reveal itself as a chorus of distant thunder. These are the fast radio bursts, or FRB, and they make even the most powerful stellar explosions seem slow and clumsy. Imagine the entire energy output of our sun, not over its 10 billion year lifetime, but compressed into a single, blinding millisecond. That is the raw, staggering power of a fast radio burst. First identified in archived data from 2007, these signals are not whispers from our galactic neighborhood. They roar across billions of light years, from galaxies so far away their light is a fossil from when the universe was half its current age. For years after their discovery, a cloud of skepticism hung over them. Could they be some bizarre glitch in our own technology, a microwave oven on the observatory campus, or an atmospheric anomaly? But as more telescopes tuned in, the evidence became undeniable. The universe was firing off unimaginably powerful radio bullets, and we were just beginning to catch them. The central mystery is one of scale and time. What natural engine in the cosmos can possibly gather that much energy and release it all in a flash shorter than the blink of an eye? The forces involved dwarf anything in our solar system or even our galaxy. Neutron stars, the dense corpses of dead suns, are prime suspects with their intense magnetic fields capable of star quakes. Some scientists theorize about collisions between these ultra-dense objects or matter falling into black holes. Yet the plot thickens with a crucial distinction. Most FRBs are one-off events, a single catastrophic boom echoing across the cosmos, but a growing number are repeaters. They fire once, go silent for days or months, and then fire again from the exact same spot in the sky. This repetition rules out any single destructive cataclysm like a collision. Instead, it points to a source that survives its own outburst, a cosmic engine that can crank itself up to impossible energies over and over again. So we are left with two intertwined puzzles. What is the catastrophic trigger for the one-time bursts, and what is the durable, reloading mechanism behind the repeaters? Each new detection narrows the possibilities while deepening the awe. The discovery of a repeating signal shattered one of astronomy's deepest assumptions. It was called FRB 121102, and it changed everything we thought we knew about these cosmic flashes. This was not a single catastrophic boom. It was a source that kept talking. Located in a tiny, faint dwarf galaxy a staggering 3 billion light-years from Earth, this object would fire off a brilliant millisecond burst, then fall silent. Weeks or months later, it would fire again and again. This repetition was the crucial clue. It meant the source of these bursts was not destroyed in the event. You cannot have a star collide with another star more than once, so whatever was making FRB 121102 had to be a durable engine, a cosmic machine that could reload and fire over immense timescales. This pointed scientists squarely at some of the most extreme objects in the universe, neutron stars, specifically a special class known as magnetars. A magnetar is a neutron star with a magnetic field so powerful it could strip the information from every credit card on Earth from halfway across the galaxy. Theorists suggest that star quakes on the surfaces of these magnetars, or sudden rearrangements of their impossibly strong magnetic fields, could crackle with enough energy to produce the burst. The repeating pattern could be explained by a magnetar periodically building up and releasing stress, like a tectonic plate on a stellar corpse. Yet, the sheer power required to make a flash visible from 3 billion light-years away pushes even this wild idea to its limits. This persistent gap between what we know is possible and what we observe has inevitably led to more speculative ideas. Could such precise, repeating, and energetically extravagant signals be the signature of something else? Some have cautiously proposed that if an advanced civilization wanted to propel interstellar light sails across the galaxy, they might use a focused beam of energy, a kind of cosmic lighthouse. From our distant vantage point, that sweeping beam might look like a repeating, milliseconds-long flash each time it pointed in our direction. While this is not the leading scientific explanation, it underscores a profound truth. FRB 121102 forces us to confront the limits of our physics. We are listening to a machine, natural or otherwise, whose operating manual is written in a language we do not yet understand. But if magnetars were the true source of these cosmic firecrackers, we needed to catch one in the act close to home. That moment arrived in April of 2020, from a familiar object within our own Milky Way galaxy, a known magnetar named SGR 1935+2154, a brilliant flash erupted. This was FRB 2020-00120E, and it was a revelation. For the first time, telescopes around the world and in space witnessed a magnetar producing a fast radio burst. The link was no longer theoretical, it was observational fact. The mystery of the engine had been solved, at least in part. We finally had a smoking gun in our own galactic backyard. Yet, this breakthrough came with a new and profound puzzle. The burst from our galactic magnetar was powerful, yes, but it was 1,000 times weaker than the faintest extragalactic fast radio bursts we detect from other galaxies. Think of it like this: we heard a nearby firecracker pop, and for a moment we understood the mechanism. But that knowledge only made the distant thunderclaps, the ones from billions of light years away, seem even more impossible. If our local magnetar represents the standard model, what cosmic supercharger exists in those distant dwarf galaxies to amplify the signal 1,000-fold? Are those faraway magnetars simply born with even more intense magnetic fields, true monsters among monsters? Or is there an environmental factor at play, perhaps a dense nebula of particles surrounding the star that acts like a natural amplifier? The detection confirmed the what, but it deepened the mystery of the how and the why. We now know the type of cosmic actor that can take the stage, but we are left wondering what extraordinary script, written in the laws of extreme physics, allows some to deliver a performance of such staggering, universe-spanning power. The galactic magnetar's faint pop only magnified the scale of the true cosmic detonations. To understand how far we have come, we must return to the very beginning, to the signal that started it all, hidden in plain sight. In 2007, astronomer Duncan Lorimer and his student were sifting through old data from the Parkes Radio Telescope in Australia, archives from the year 2001. Their goal was to find new pulsars, the steady ticking clocks of dead stars. Instead, they found an anomaly, a single 5-millisecond burst of radio waves, so intense it saturated the telescope's receiver. It was not a steady pulse, it was a spike, a solitary scream in the data. The signal was so bright and so brief that for years it was dismissed. Surely, the reasoning went, this was just terrestrial interference, a glitch from a passing satellite or a piece of electronic equipment on the ground. It was filed away, a cosmic curiosity not worthy of a major headline. This signal, now known as the Lorimer burst, would become the progenitor of an entire new field of astrophysics, but its acceptance was a battle. The central problem was a property called dispersion. As radio waves travel across the vast interstellar and intergalactic medium, they are slowed down by free electrons. Higher frequencies arrive at our telescopes just a fraction of a second before the lower frequencies. This smearing effect is measurable. By calculating the dispersion, astronomers can estimate how much material the signal has traveled through and therefore how far it has come. The dispersion measure for the Lorimer burst was enormous. It pointed to a journey through an immense amount of cosmic stuff, far beyond the thin halo of our own Milky Way. The signal had to be extragalactic, originating from a source billions of light years away. That conclusion was so revolutionary, so challenging to the known limits of physics, that the scientific community met it with deep skepticism. It took years of debate and the discovery of more bursts for the truth to solidify. We had not found a local glitch. We had captured the first faint echo of a cosmic catastrophe so powerful it could be seen across the universe. The Lorimer burst was the first witness to a hidden, violent reality, a single data point that forced us to rewrite the chapters on cosmic energy. The Lorimer burst was a solitary clue, but to solve a mystery this vast, you need a flood of evidence. That deluge arrived with a new kind of telescope, one built not with a single giant dish, but as a stationary array of metal cylinders in the mountains of British Columbia. The Canadian Hydrogen Intensity Mapping Experiment, or CHIME, was designed for an entirely different purpose, to map the cosmic web of hydrogen throughout the universe's history. Yet, by pure ingenious design, it also became the most prolific hunter of fast radio bursts the world has ever known. Unlike traditional telescopes that stare at a tiny patch of sky, CHIME sees an enormous swath of the heavens every single day. It is the ultimate cosmic net, and almost immediately it began catching FRBs by the dozens, then the hundreds. This was a revolution in scale. Where once these bursts were rare curiosities, they are now understood to be a constant cosmic drumbeat, with thousands likely happening across the sky every single day. This tidal wave of data allowed scientists to move from wondering what FRBs are to classifying them, sorting them into families. they found more repeaters, confirming that many sources are not one-time explosions. They began to trace the bursts back to their home galaxies, revealing they come from all types of cosmic neighborhoods, from ancient dwarf galaxies to massive spirals. But within this flood, CHIME caught something truly extraordinary, a signal that stood out even among the strange. It was a repeater known as FRB 180916 that did not fire at random. Its bursts followed a clear, predictable cycle. For roughly 4 days it would be active, spitting out bursts. Then for 12 days it would fall completely silent. This 16-day pattern repeated with clockwork precision. A periodic signal like this is a golden clue. In astronomy, periodicity almost always points to an orbit. The silence could be when the object is eclipsed by a companion, or when its beam of radiation is pointed away from us. This suggests the FRB source is not alone. It is locked in a gravitational dance with another massive body, perhaps a companion star or a black hole. We are no longer just listening to a mysterious explosion. We are beginning to map the architecture of the machine causing it. The sheer volume from CHIME gave us a census, but this one rhythmic repeater gave us a blueprint, a first glimpse into the intricate celestial mechanics behind the universe's most powerful flashes. While CHIME revealed the rhythmic patterns of deep space, another telescope was witnessing a star behaving in a way that defied every known law of stellar physics. Far from the crackle of radio bursts, this mystery played out in the ancient language of light itself. The Kepler Space Telescope, a silent sentinel orbiting our Sun, had one mission: to stare at a single patch of the Milky Way and monitor the subtle, rhythmic winks of distant stars. It was hunting for planets by catching the tiny, predictable dip in starlight as they passed in front of their suns. In the constellation Cygnus, it found a star catalogued as KIC 8462852, but the world would come to know it as Tabby's star, named for the astronomer Tabitha Boyajian who first sounded the alarm. The data from Kepler was not just unusual, it was impossible. Instead of the gentle, periodic dips of an orbiting planet, Tabby's star plunged into darkness erratically and dramatically. Its light would drop by a staggering 22% at times, a depth that meant something colossal was blocking its face. To put that in perspective, if Jupiter, our solar system's giant, passed in front of our Sun, it would cause a dimming of only about 1%. Whatever was orbiting Tabby's star was not a planet. It was something on a scale that rewrote the textbooks. The dimming was also deeply irregular. There was no clean, repeating clockwork orbit. The star would dim sharply for days, then brighten, then dip again in a chaotic, asymmetric pattern that suggested a vast, uneven swarm of objects. Scientists scrambled for natural explanations. Could it be a gigantic family of comets, millions of them, breaking apart and casting immense shadows? Perhaps it was the debris from a catastrophic planetary collision, a cloud of dust and rock slowly spiraling into the star. Yet each theory strained against the data. The sheer amount of material required to block that much light was almost implausible, and no known natural process could easily create such a jagged, unpredictable shadow. It was this profound failure of conventional astronomy that opened the door to a staggering, speculative idea. In the 1960s, physicist Freeman Dyson theorized that an advanced civilization, having consumed the energy of its home planet, might eventually seek to harness the total output of its star. They would construct a vast swarm of energy collecting satellites or habitats, a Dyson swarm encircling their sun. From an immense distance, such a megastructure under construction, with panels and orbitals in chaotic, uneven orbits, would look exactly like what Kepler saw, a star with bizarre, deep, and irregular dimming patterns. The hypothesis was not a claim, but a question born of sheer desperation to explain the observations. It forced a profound and humbling line of inquiry. When we exhaust all natural explanations for a phenomenon, at what point do we dare to consider an artificial one? Tabby's star remains an enigma, a silent optical signal that challenges our certainty about what is possible in a cosmos we are only beginning to understand. For all the grandeur of cosmic mysteries, some of the most puzzling signals turned out to have a startlingly humble origin, a lesson in scientific humility written in kitchen appliances. In the early hunt for fast radio bursts, astronomers at Australia's Parkes Observatory kept detecting bizarre signals they called puritans. Named after mythical winged stags that cast the shadows of men, these signals were perfect imposters. They had the exact same dispersed, smeared signature that pointed to a long journey through intergalactic space, the hallmark of a genuine FRB. Yet they had one critical flaw: they were only ever detected when the massive Parkes dish was pointed in one specific direction, and they always appeared during local daytime hours. This was a clue that the source was not cosmic but terrestrial, something right here on Earth. The mystery became a scientific detective story. Teams ruled out aircraft, satellites, and ground-based radar. They even considered lightning and atmospheric events, but nothing fit the precise profile. The breakthrough came when someone realized the signals correlated with lunch times at the observatory. The culprit, after years of investigation, was embarrassingly mundane: the microwave ovens in the observatory's staff kitchen. When a hungry researcher heated their meal and then opened the oven door before the timer had fully finished, the safety mechanism would release a brief, powerful burst of radio waves. That burst would zip out the door, bounce off the observatory's metal structures, and travel straight up into the giant, sensitive dish of the radio telescope itself. The telescope, designed to listen to the faintest whispers of the cosmos, was perfectly capturing the impatient hunger of its own operators. The Puritan saga is far from a scientific failure. It is a masterclass in the rigorous process of discovery. It underscores a fundamental truth in the search for cosmic signals. The first and most difficult task is to rule out our own noisy, inventive, and often hungry civilization. Every strange blip in the data must survive this gauntlet of scrutiny before it can earn the title of a true mystery from the deep. The search for intelligence among the stars has always been a game of patience and pattern recognition, sifting an ocean of noise for a single, perfect note. In 2003, it seemed the SETI at Home project, which used the idle processing power of millions of personal computers around the world, might have found one. Volunteers scanning data from the massive Arecibo radio telescope noticed a faint but persistent signal, catalogued as SETI 02+14a. On paper, it was a compelling candidate. It pulsed at a frequency of about 1,420 MHz, the natural emission frequency of hydrogen, the most common element in the universe. This is a quiet channel in the cosmic radio spectrum, a logical place for a civilization to plant a beacon, a universal watering hole where anyone listening might tune in. Furthermore, the signal exhibited a slight drift, a change in frequency over time. This drift was exactly what you would expect if the signal originated from a planet rotating on its axis and orbiting its star, causing a subtle Doppler shift as it moved relative to Earth. It passed through many of the project's automated filters designed to weed out terrestrial interference and natural cosmic static. The source, however, was the most puzzling part. It appeared to originate from a point in the sky between the constellations Pisces and Aries, a region that seemed utterly empty. No nearby stars, no known planets, just a seemingly blank void. This faint whisper from nowhere sparked immediate controversy and excitement. Had we finally heard a deliberate transmission? The answer, frustratingly, remains maybe. Despite its promising parameters, the signal was incredibly weak, hovering right at the threshold of detection. Every attempt to find it again, to confirm its existence with other telescopes, has failed. It vanished as mysteriously as it appeared. Some scientists argue it was likely just an artifact of exceptional noise, a random fluctuation that, by sheer chance, mimicked the signature of an artificial signal. Others maintain its specific properties make that statistically very unlikely. SHB02 plus 14 exists in a frustrating limbo, too perfect to dismiss outright but too elusive to ever verify. It stands as a ghost in the machine, a reminder that in the grand search, the most tantalizing clues are often those that refuse to ever show themselves twice. The search for a single perfect note often reveals a rhythm instead, a beat so steady it feels like intelligence itself. This brings us to the story of the first pulsar, a discovery that perfectly captures the thrilling ambiguity between natural wonder and artificial design. In the late 1960s, a young graduate student named Jocelyn Bell Burnell was helping to build a new radio telescope in Cambridge, a forest of wooden poles and wires designed to study the twinkling of distant quasars. As she meticulously analyzed the miles of paper chart recordings the telescope produced, she noticed a peculiar recurring scratch. It was not the broad, fuzzy signal of a quasar. It was a sharp, precise pulse, repeating every 1.337 seconds with a regularity that was utterly unnatural. The signal, coming from a fixed point in the constellation Vulpecula, was catalogued as CP1919. To Bell Burnell and her supervisor Anthony Hewish, its machine-like perfection was immediately baffling. They jokingly labeled it LGM-1 for Little Green Men 1. The possibility, however fleeting, was genuine. Could this be a beacon, a cosmic lighthouse built by a civilization to mark its presence? The pulses were too fast and too regular to be anything from a variable star, and nothing known in astrophysics could account for such a perfect celestial metronome. For a few tense months, they secretly investigated the signal, even checking if it could be some unknown human-made interference or a signal from an extraterrestrial probe. The resolution came not from finding aliens, but from uncovering a new, breathtaking class of natural object. The source was a rapidly spinning neutron star, the collapsed, ultra-dense core of a massive star that had died in a supernova. As this stellar corpse spins, beams of intense radiation shoot from its magnetic poles. If those beams sweep across Earth like the beam of a lighthouse, we see a flash with every rotation. CP1919 was the first of these cosmic pulsars ever identified. The discovery was a monumental lesson. It proved that nature, under the most extreme conditions, could manufacture signals of astonishing precision, signals that perfectly mimic the kind of orderly pattern we might associate with a transmitting intelligence. This moment set a crucial precedent for every mystery that followed, from the wow signal to the fast radio bursts. It taught scientists to first look for the natural, albeit wildly exotic, explanation. But it also permanently wired into the search a tantalizing question. If a spinning cinder of a star can impersonate an alien clock, what other impossibly precise rhythms might be waiting in the data, and will we know the difference when we finally hear one? The pulsar's discovery established a vital rule: always suspect nature's ingenuity first. Yet when a signal arrives from our very own cosmic backyard, that rule is tested with electrifying intensity. In December of 2020, the Breakthrough Listen project, the most ambitious search for extraterrestrial intelligence ever undertaken, announced a detection that sent a shockwave through the scientific community and the public imagination. They had found a signal they named BLC1. What made this signal so instantly captivating was not just its properties, but its address. It appeared to originate from the direction of Proxima Centauri, the closest star to our own Sun, a mere 4.2 light-years away. This is a red dwarf star we know hosts at least one rocky planet, Proxima Centauri b, nestled in its habitable zone where liquid water could exist. For a moment, it seemed a whisper might have come from the nearest possible world beyond our solar system. The signal itself was a textbook candidate. It was a narrowband radio emission, meaning all its energy was concentrated in a very specific sliver of the radio spectrum, like a pure musical note against a background of static white noise. This is a hallmark of artificial transmission, as natural cosmic processes almost always produce broadband noise. Furthermore, the signal exhibited a drift, a slow, smooth change in frequency over time. This drift matched precisely what you would expect if the source was on a planet orbiting its star, the motion causing a subtle Doppler shift, like the changing pitch of a passing ambulance siren. It was as if the signal carried the fingerprint of a technological origin and the orbital signature of a world. The excitement was palpable and understandable. Had we, against all odds, detected a leak from a civilization next door, the Breakthrough Listen team, however, was meticulously cautious. They followed a rigorous protocol of verification, checking and rechecking the data against every possible source of interference. The sobering truth emerged after months of intense analysis. The signal's characteristics, while perfect on paper, were ultimately too perfect. Its frequency aligned suspiciously well with common oscillators found in everyday human electronics. The most likely explanation was that BLC1 was not a message from Proxima b, but a faint echo of our own technological noise, a radio signal from a device on or near Earth that had been reflected off some piece of space debris or a satellite, creating the illusion of a celestial origin. It was a profound lesson in cosmic irony. The very qualities that made it a perfect candidate were also the clues to its terrestrial nature. This episode did not diminish the search, it refined it. It underscored the immense challenge of finding a true needle in a cosmic haystack when we are surrounded by a growing fog of our own digital whispers. The nearest star had offered not a greeting, but a masterclass in humility, reminding us that the greatest obstacle to hearing another civilization may be learning to truly silence our own. The search for a signal from our nearest star ended in earthly noise, but another red dwarf soon presented a riddle that was harder to dismiss. In 2017, astronomers at the mighty Arecibo Observatory turned their giant dish toward a quiet, nearby star called Ross 128. This faint red dwarf is just 11 light-years away, a stone's throw in cosmic terms, and it was being studied for the subtle signs of flares that could strip atmospheres from any orbiting planets. What they found, however, was not a typical stellar tantrum. Over a 10-minute period, the telescope recorded a series of bizarre, drifting signals. They were quasi-periodic, meaning they had a rough, repeating rhythm, but one that was messy and distorted. They occupied a frequency band not usually associated with natural stellar activity, and they seemed to come only from the direction of Ross 128, not from any other stars observed that same day. This was not the clean, narrowband whisper of a potential transmission, but it was equally perplexing. It did not match the profile of a solar flare, which typically bursts across a wide range of frequencies and then fades. This was something else entirely, a strange, repetitive chatter from a seemingly quiet star. The astronomy community was genuinely stumped, and for a brief, exciting period, even the possibility of an unknown natural phenomenon from the star itself was on the table. The resolution, once again, came from looking not out into the cosmos, but down toward our own orbit. The leading hypothesis that emerged was interference, not from a microwave oven this time, but from something much farther away and more systematic. The signals, scientists concluded, were most likely caused by one or more geostationary satellites. These are the satellites that hang in a fixed position over Earth's equator, providing television, weather data, and communications. From the perspective of the giant, unmoving Arecibo dish, as it tracked Ross 128 moving across the sky, its beam would have swept through the distant orbital paths of these satellites. Their transmissions, reflected and distorted by the complex geometry, could have created the odd, drifting, quasi-periodic pattern that perfectly mimicked a celestial source. The Ross 128 anomaly stands as a critical marker in our time. It is a stark reminder that the frontier of cosmic discovery is no longer just the silent vacuum of space. It is now surrounded by a bustling shell of our own making. Every new satellite we launch, every new signal we broadcast, adds another layer of static to the window through which we peer into the universe. Finding a true signal from the stars is becoming a game of listening for a whisper in an increasingly crowded and noisy room. Our own noisy neighborhood makes the search for a true cosmic whisper all the more difficult. But what if the signal we are seeking is not a radio transmission, but a breath? A faint chemical signature written in the light of a distant sun. This brings us to a world called K218b, and a detection that changed the language of the search for life itself. Orbiting a cool red dwarf star about 110 light-years away in the constellation Leo, this planet is not just another exoplanet. It is a super-Earth, a world about 8 times the mass of our own, and it resides squarely within its star's habitable zone, that temperate band where water could exist as a liquid on the surface. In 2019, data from the Hubble Space Telescope revealed something extraordinary. By carefully analyzing the starlight that filtered through the planet's atmosphere as it passed in front of its star, astronomers detected the unmistakable spectroscopic fingerprint of water vapor. This was not an inference or a hopeful model. It was a direct observation, the first time water vapor had ever been confirmed in the atmosphere of a habitable zone world beyond our solar system. The implications are staggering. For decades, the mantra in astrobiology has been follow the water. Liquid water is the universal solvent, the essential ingredient for biochemistry as we know it. Finding its vapor in the air of a temperate world is like seeing humidity in the sky of an alien planet, a sign that the most fundamental condition for life might be met. But the discovery of water vapor is only the opening sentence of a much longer story. K218b is a profoundly alien place. Its large size suggests it may be more of a mini Neptune, a world with a thick, hydrogen-rich atmosphere and a possible global ocean under immense pressure rather than a rocky twin of Earth. The presence of water does not mean lakes and rivers. It could mean a steamy, high-pressure envelope where the very nature of chemistry is different. This is where the signal becomes a roadmap for the future. The Hubble detection was a monumental first step, but Hubble's vision is limited. To read the next chapter, we need a telescope capable of discerning the finer details of that alien air. This is the mission of the James Webb Space Telescope. With its vastly more powerful infrared eyes, Webb can look beyond the water vapor. It can search for other molecules, potential biosignatures like methane, which on Earth is largely produced by living organisms, or oxygen, which in large, unstable quantities often points to biological activity like photosynthesis. The signal from K218b is not a message but an invitation. It is a chemical whisper saying, "Look closer." The next generation of observations will tell us if this distant atmosphere holds only the simple chemistry of a strange world, or if it carries the complex, unstable fingerprints of something far more remarkable. We are no longer just looking for planets, we are beginning to taste the air of other worlds. While chemical whispers hint at distant oceans, our own galaxy holds a monument to its own explosive history, written in the silent language of pure energy. Billowing from the heart of the Milky Way, 2 colossal orbs of gamma radiation stretch for 25,000 light-years above and below the galactic plane. These are the Fermi bubbles discovered in 2010 by the Fermi Gamma Ray Space Telescope. To grasp their scale, picture this: if our eyes could see this high-energy light, the bubbles would dominate half the night sky, each one a vast, faintly glowing lobe emanating from the central black hole. They are not a sudden flash, but a persistent, diffuse hum, a ghostly afterglow of some ancient cataclysm. The mystery lies in what caused them. One leading theory points to our galaxy's central supermassive black hole, Sagittarius, a star. While quiet today, it may have had a violent feeding frenzy in the past, perhaps devouring a large cloud of gas. The immense energy released in such an event could have blasted out jets of material at near light speed, inflating these gigantic bubbles over millions of years. An alternative theory suggests a different kind of frenzy, a period of runaway star formation in the crowded galactic center. If hundreds of massive stars were born and then died in supernova nearly simultaneously, their combined stellar winds and explosions could have pumped enough energy into space to carve out these structures. The faint gamma-ray signal we detect today is the fading echo of that energy, still trapped within the bubble walls. So the Fermi bubbles present us with a cosmic crime scene, but the culprit has left the scene millions of years ago. Are we looking at the relic of a black hole's forgotten tantrum, or the collective death cry of a generation of stars? This silent hum is a direct signal from our galaxy's adolescence, a reminder that even the seemingly steady spiral we call home has a deeply violent past. The faint gamma-ray hum of the Fermi bubbles is not the only ghost haunting our galactic core. When we zoom in with radio telescopes, the center reveals a tapestry of even stranger threads. Stretching across the chaotic heart of the Milky Way are mysterious structures known as the galactic center radio filaments. Imagine looking up at a night sky not of stars, but of luminous, impossibly long hairs, each one a thread of pure energy. These are not solid objects, but lines of force made visible. They are long, thin streams of what scientists call synchrotron radiation, a special kind of light emitted when high-speed electrons spiral at nearly the speed of light around powerful magnetic field lines. It is the universe's way of drawing its own magnetic blueprint in the sky. What makes these filaments so baffling is their sheer scale and order. Some stretch for over 100 light-years in length, yet they are astonishingly thin, only about 1 light-year wide. They often stand rigid, aligned perpendicular to the flat plane of the galaxy itself, like the bristles on a cosmic brush pointing directly away from the central black hole. Their precise orientation and needle-like structure defy the turbulent chaos of the galactic center, where gas clouds collide and stars are born in violent bursts. How can such delicate, orderly threads survive in this cosmic maelstrom? Their origin is one of the great unsolved puzzles of our own backyard. The leading theory connects them directly to the immense gravitational and magnetic powerhouse at the core, Sagittarius, a star. The thinking is that these filaments are like cosmic scars or tracer lines, marking where vast outflows of material from past black hole activity have stretched and ordered the galaxy's magnetic fields. They could be the lingering aftermath of a gigantic jet that punched out of the core millions of years ago, leaving behind magnetized rails where electrons still race and glow. Or perhaps they are formed by the interaction of colossal cosmic winds with the dense molecular clouds that litter the center. Each filament is a unique and poorly understood form of cosmic architecture, a natural particle accelerator suspended in space. They remind us that the forces shaping galaxies are not just gravity and explosion, but also magnetism on a scale we are only beginning to map. These silent, glowing threads are clues to the hidden skeleton of the Milky Way, a magnetic fingerprint left by the sleeping giant at its heart. While the galactic center reveals its magnetic skeleton, a discovery from the edge of the observable universe suggests our entire cosmic neighborhood might be caught in a current. In 2008, a team of astronomers studying the oldest light in existence, the cosmic microwave background, stumbled upon an anomaly that, if real, would rewrite cosmology. They called it the dark flow. This was not a flash or a pulse, but a subtle, statistical drift in the motion of entire galaxy clusters. By carefully mapping the microwave background, the faint afterglow of the Big Bang, scientists can measure how galaxy clusters move through space. The expectation was that this motion should be random, a chaotic drift in the aftermath of the universe's birth, yet the data told a different story. It appeared that over 1,000 massive clusters scattered across billions of light years were all streaming in the same direction like leaves caught in a cosmic river. This motion was not caused by any visible mass in our universe. The gravitational pull of every known galaxy, every filament of dark matter in the cosmic web, had already been accounted for. Something else, something immense and unseen, was tugging on them. The implication was staggering. One radical explanation proposed that the dark flow was evidence of a gravitational influence from beyond our observable universe. Our cosmos, the entire expanse born from the Big Bang, might be just one bubble in a vast multiverse. If another universe bubble existed incredibly close to our own in a higher dimensional space, its mass could exert a gravitational pull on our entire domain, creating this coordinated drift. Alternatively, the flow could point to a colossal, unseen structure, a supercluster of matter so vast it lies beyond the cosmic horizon, its shadow only perceptible through its tug on everything we can see. The scientific community met this claim with intense skepticism, as it must. Later analyses with more precise data from missions like the Planck satellite failed to confirm the original detection, casting deep doubt on the dark flow's existence. Many now consider it a likely statistical fluke, an artifact of how the difficult measurements were processed, yet its legacy endures as a profound question. If such a flow were ever confirmed, it would mean our universe is not an island. We would have received the first possible signal from a realm beyond our own, a silent tide hinting at a reality vaster than we ever dreamed. The grandest signals pull at entire galaxy clusters, but sometimes the most telling mysteries are found in the smallest of drifts. For decades, two robotic pioneers carried a secret in their silent flight. The Pioneer 10 and Pioneer 11 spacecraft, after their historic missions to Jupiter and Saturn, became the first human-made objects on a trajectory to leave our solar system entirely. As they sailed into the dark, scientists tracking their precise positions noticed something deeply wrong. Both spacecraft were slowing down, not from the gentle tug of distant stars or the drag of solar wind, but by an amount so tiny and so constant it defied all known physics. It was an anomalous acceleration, always directed back toward the sun, as if an invisible hand had reached out and was ever so gently applying the brakes. This was the Pioneer anomaly. The numbers were maddeningly precise. The deceleration was just under 9 nanometers per second squared, a force so minuscule it is like comparing the weight of a single snowflake to a mountain. Yet, over years and then decades of travel, this tiny, unaccounted-for push added up, throwing the spacecraft hundreds of thousands of kilometers off their predicted courses. The signal was not a flash of light or a burst of radio waves. It was a whisper written in orbital mechanics, a persistent deviation that would not go away. The implications were profound. Could this be the first measurable hint of new physics? Perhaps Einstein's theory of gravity needed a slight modification at the vast scales of the solar system. Some theorists suggested it might be evidence of dark matter's local gravitational pull, or even a sign of a fundamental misunderstanding about inertia itself. The Pioneer anomaly became a thorn in the side of classical physics, a tiny data point with the potential to topple giants. Solving it required a detective story that spanned a generation. The original engineers who built the probes had retired. Technical documents were archived or lost. A dedicated team of scientists acting as cosmic forensic archaeologists had to reconstruct the spacecraft from blueprints and old memos. They modeled every conceivable force, from the gentle pressure of sunlight to the tiny leakage of gas from thruster valves. They calculated the gravitational pull of every planet and even the Kuiper belt. Nothing accounted for that steady, sunward tug. The breakthrough came from thinking not about the void the probes were traveling through, but about the probes themselves. The Pioneers were powered by radioisotope thermoelectric generators, nuclear batteries that produced heat and converted it to electricity. That heat had to go somewhere. The team realized the spacecraft's design was not perfectly symmetrical. The heat radiating from the electronic systems and the generators themselves did not flow out evenly in all directions. More thermal radiation was being emitted from the back of the spacecraft, the side facing away from the direction of travel. This anisotropic or directionally lopsided radiation acted like a tiny photon rocket. Every photon of heat carrying momentum away from the rear of the probe gave it a minuscule push forward. But because the spacecraft were oriented with their main antennae always pointed back at Earth, which was essentially toward the Sun, this gentle push from escaping heat was actually a deceleration, a tiny brake applied by the spacecraft's own warmth. The team ran the exquisitely detailed calculations, factoring in the exact paint, the geometry of the equipment panels, and decades of thermal history. The numbers aligned, the Pioneer anomaly vanished. The mysterious constant acceleration was not a flaw in our laws of gravity, but a testament to the power of a forgotten engineering detail. The signal was real, but its source was heartbreakingly human. It was the faint thermal signature of our own technology, a reminder that sometimes the universe's most puzzling whispers begin as echoes in the machine. The Pioneer probes taught us to question our own machines first, but what happens when the mysterious object is not ours at all? In October of 2017, a point of light moving against the stars revealed a visitor from a place no human eye had ever seen. The Pan-STARRS telescope in Hawaii spotted it first, a faint speck hurtling past the sun at blistering speed. Astronomers named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. This was not just another asteroid from our own solar system. Its trajectory was hyperbolic, a steep, open arc that could only mean one thing. Oumuamua was the first confirmed object from interstellar space ever observed passing through our cosmic neighborhood. Its origin was a star system far beyond our own. The data painted a portrait of a truly alien wanderer. It was dark red, tinged by eons of cosmic radiation. Most strikingly, its brightness varied dramatically as it tumbled, suggesting an extreme, elongated shape, perhaps 10 times as long as it was wide. Imagine a cosmic cigar or a flattened pancake tumbling end over end through the void. But the real mystery was not just its shape, it was how it moved. As Oumuamua swung around the sun and began its journey back out into interstellar space, something impossible happened. Its trajectory did not follow a perfect gravitational curve. Precise tracking showed it was accelerating ever so slightly as it departed. This was a non-gravitational acceleration, a push that could not be explained by the sun's pull alone. For a comet, such a boost is common, caused by outgassing. As the icy nucleus heats near the sun, it vents gas and dust, creating a visible coma and tail that act like a natural rocket engine. Yet Oumuamua showed no coma, no tail, no visible signs of outgassing whatsoever. It was as dry and inert as a rock, so what was pushing it? The scientific scramble began. One leading theory proposed it was a comet after all, but an exotic one. Perhaps it was composed of very pure hydrogen ice or solid nitrogen, ices that could sublimate, turning directly from solid to gas, without releasing the dusty debris that forms a traditional tail. This hidden outgassing could provide the gentle thrust. Others suggested it could be a fragment of a Pluto-like world, a shard of nitrogen ice knocked loose in some ancient collision. Yet the required explanations felt strained, like fitting a square peg into a round hole of data. Into this uncertainty stepped a provocative idea from Harvard astronomer Avi Loeb. He argued that the most straightforward explanation, given the object's peculiar acceleration and its unusual shape, was that Oumuamua could be a piece of advanced technology, a light sail. A light sail is a proposed method of interstellar travel where a thin, reflective sheet uses the pressure of starlight for propulsion, much like a boat sail uses wind. Loeb suggested Oumuamua's flat, pancake-like geometry and its precise sun-driven acceleration were consistent with a discarded light sail drifting between the stars. The scientific community reacted with intense debate. Many astronomers firmly rejected the artificial hypothesis, insisting extraordinary claims require extraordinary evidence, and that a natural explanation, however unusual, was far more likely. They pointed out we had never seen an interstellar object before, so of course the first one would surprise us. The debate over Oumuamua was never really about proving it was an alien spacecraft. It was a profound collision between scientific caution and cosmic curiosity. It forced a fundamental question in a universe full of wonders. At what point does our insistence on known natural causes become a limitation to discovery? Oumuamua has now vanished into the dark, carrying its secrets with it. It was a fleeting signal, a one-line message in the celestial ledger that read, "We do not know everything that is out there." Its legacy is the crack it opened in our imagination, a reminder that the most unsettling mysteries are sometimes those that pass right through our front yard, silent and swift, before we even learn how to ask the right questions. Oumuamua's silent passage hints at a cosmos filled with unseen architects, but the most profound blueprint of all is written across the entire sky in a faint, ancient light. This is the cosmic microwave background, the cooled remnant of the universe's first fiery moment. It is the oldest signal we can detect, a snapshot of the infant cosmos just 380,000 years after the Big Bang. For the most part, this afterglow is remarkably uniform, a smooth sea of microwaves with only tiny, expected fluctuations. But in 2004, astronomers mapping this sea with the WMAP satellite found a blemish, a region so cold and so large it should not exist. They called it the cold spot. Located in the constellation Eridanus, this area is a staggering 1.8 billion light-years across, and it is about 70 microkelvins colder than the average background temperature. That difference sounds minuscule, but on the scale of the universe's smooth early glow, it is a glaring anomaly, a cosmic bruise that defies easy explanation. The standard model of cosmology, which beautifully explains so much of what we see, struggles to account for this cold spot. The tiny temperature variations we usually see are believed to be seeds, the gravitational fingerprints that eventually grew into galaxies and clusters. But the cold spot is far larger and colder than those primordial seeds should allow. It is an outlier, a statistical improbability that has forced scientists to consider extraordinary possibilities. The leading natural theory proposes that the cold spot is not a feature of the ancient background light itself, but a trick of the light played by a vast emptiness along our line of sight. Imagine the cosmic microwave background as a distant glowing wall. If on its journey to us that light must pass through an enormous region of space with far fewer galaxies and less dark matter than average, a cosmic supervoid, the light would lose a tiny amount of energy climbing out of that underdense region's gravitational well. This effect, called the integrated Sachs-Wolf effect, would make that patch of the sky appear cooler. The problem is scale. To create a cold spot this size, the void would need to be unimaginably vast, perhaps the largest structure ever identified in the universe. While some evidence for a sparse region in front of the cold spot exists, it does not seem nearly large or empty enough to explain the full effect. The numbers, once again, do not quite add up. This failure of conventional explanations has opened the door to a truly mind-bending alternative. Some cosmologists have proposed that the cold spot could be the imprint of a collision with another universe. In the multiverse framework, our universe is one bubble in a frothing, infinite metacosmos. If another bubble universe brushed against our own in the distant past, the energy of that collision could have left a scar on our cosmic microwave background, a circular region of altered temperature, a cold spot. It is a hypothesis that stretches the limits of testable science, yet it emerges from a simple, haunting question. If all the mundane explanations fall short, what does that leave? The cold spot stands as a humbling reminder. The very first light of creation, the signal that confirmed the Big Bang and launched modern cosmology, still contains puzzles that point to frontiers beyond our current understanding. It whispers that the story of our universe's birth may have chapters we have not yet dreamed of, written in the faint chill of an ancient sky. That ancient chill on the cosmic background is a testament to hidden histories, and sometimes those histories leave behind a ghost in the radio spectrum. Drifting in the cosmic deep, astronomers found a shape that earned the name Dragonfly. This is not a galaxy of stars as we know it, but a colossal, diffuse cloud of radio emission, a faint, wispy silhouette against the darker void. Its discovery was a surprise, a patch of radio light that did not correspond to any bright visible galaxy or known cataclysm. It simply hangs in space, a galaxy-sized whisper. The Dragonfly defies our standard catalogue of celestial objects. It is not an active galactic nucleus, those brilliant engines powered by supermassive black holes. It lacks the intense, compact core that characterizes such powerhouses, nor is it the classic remnant of a supernova, which are typically smaller and show clear signs of an expanding shockwave from a single stellar death. This object is too large, too calm, and too amorphous. It appears instead as a fading echo, the lingering aftermath of a titanic event that has long since passed into silence. One compelling theory suggests we are seeing the ghost of a past galactic merger. When two galaxies collide in a slow, billion-year dance, their central black holes can eventually spiral together and merge, releasing a tsunami of gravitational waves. That unimaginable convulsion could have violently stirred the galaxy's magnetic fields and hurled clouds of charged particles far into intergalactic space. Over eons, those particles would lose energy, radiating this faint, diffuse radio glow we now catch like the dying embers of a cosmic fire. The Dragonfly, then, may be a fossil signal. It is the radio frequency tombstone for a catastrophic union that occurred when Earth's continents were still forming, a silent monument to a violence so complete that only its faintest reverberations remain. It challenges us to listen not just for the universe's active screams, but for its long, slow sighs. Fossil signals like the Dragonfly reveal a universe of fading echoes, but some structures are so strange they seem to defy the very idea of fading at all. In the vast radio sky, a new class of object has emerged that looks like nothing we have seen before, the odd radio circles, or ORC. Discovered by the Australian Square Kilometre Array Pathfinder, these are perfect, ghostly rings of radio emission, so enormous they could easily swallow entire galaxies. They are not visible in optical, X-ray, or infrared light, only in the specific frequency of radio waves, making them invisible to most telescopes. They hang in the dark like cosmic smoke rings, and their origin is a complete and utter mystery. Every conventional explanation has failed. They are far too large and uniform to be the remnants of a supernova. They are not Einstein rings, the gravitational lensing effects that warp distant light into circles, as there is no central galaxy massive enough to cause such a distortion. They do not match the profile of shockwaves from known galactic collisions or the energetic lobes from active black holes. They are simply there, immense and enigmatic, a new type of celestial graffiti written in a language of pure radio static. The leading hypothesis, born from a lack of any better idea, is that they could be the aftermath of a truly gargantuan event, a shockwave that propagated across intergalactic space. One possibility is a starburst on a scale so extreme it dwarfs anything in the local universe, where a galaxy experiences a frenzied burst of star formation so violent that the combined stellar winds and supernova create a spherical tsunami of particles expanding outwards. Another, even more dramatic idea is that they are the fossil imprint of a radio jet from a supermassive black hole that has long since shut off, its once powerful beam having inflated a colossal bubble that we now see in cross-section as a ring. Yet these explanations feel speculative, like trying to describe an elephant by touching only its tail. The ORCs are a humbling reminder that our maps of the cosmos are still incomplete. They are signals from a previously unseen layer of reality, phenomena that operate on scales and through mechanisms we have not yet learned to perceive. proving that even our most advanced surveys are still only sketching the outlines of the unknown. Those ghostly radio circles are a new kind of cosmic signature, but the universe is also hiding a staggering amount of its most basic building material in plain sight. This brings us to a signal defined by its absence, one of cosmology's greatest accounting errors, the missing baryon problem. Baryons are the particles that make up all the ordinary matter we know and love, the protons and neutrons in stars, planets, and our own bodies. When we tally up all the luminous matter we can see in galaxies, plus all the gas and dust we can detect, we come up woefully short. According to our best models of the Big Bang, only about half of the normal matter the universe should have created is actually accounted for in our cosmic ledger. So where did the other half go? For decades, it was a glaring gap in our understanding of cosmic structure. The leading suspect has long been a vast, diffuse web of superheated gas strung between the galaxies, known as the warm-hot intergalactic medium, or the WIM. This is not a cold, dark void, but a seething ocean of plasma, heated to millions of degrees by the gravitational energy of the cosmic web itself. It's so thin and so hot that it doesn't glow brightly in any single wavelength. It's a faint, pervasive whisper spread across the entire sky. Detecting it is like trying to spot the heat shimmer above a vast desert from 1,000 miles away. The breakthrough has come from looking not for the WIM's own light, but for the shadow it casts. Astronomers use the brightest beacons in the universe, distant quasars, as cosmic flashlights. As the intense light from a quasar travels billions of light years to reach us, it passes through these filaments of the WIM. The superheated gas absorbs specific, telltale wavelengths of that light, particularly in the ultraviolet and soft X-ray parts of the spectrum. These absorption lines are like a chemical barcode imprinted on the quasar's light, a direct signal that says, yes, this specific ion of oxygen or neon is here in this specific filament. It's a painstaking process, requiring the precise observation of hundreds of background quasars to slowly map the invisible architecture of the cosmic web. Each detection is a tiny data point, a single thread in a tapestry we are only beginning to weave. This is the slow, meticulous work of cosmic forensics, finding the missing matter not by seeing it directly, but by reading its faint signature in the light that passes through it. We are finally balancing the universe's books, proving that the ordinary stuff of creation isn't missing at all. It's just been hiding in the hottest, most elusive spaces between everything we see. Balancing the cosmic ledger of matter required a new kind of vision, but to hear the universe's most violent symphonies, we needed an entirely new sense. On September 14, 2015, a ripple in the fabric of reality itself washed over our planet. It was not a flash of light or a burst of radio waves. It was a vibration in space-time, a gravitational wave predicted by Einstein a century earlier and finally captured by the Laser Interferometer Gravitational Wave Observatory, LIGO. The signal lasted just 0.2 of a second, a tiny chirp that rose in frequency and then abruptly cut off. That fleeting whisper told a story of unimaginable violence, the final inspiral and cataclysmic merger of two black holes, one about 29 times the mass of our Sun, the other 36 times, dancing to their doom over 1 billion light-years away. In that fraction of a second, the collision converted a mass roughly 3 times that of our Sun into pure energy, rippling outward as gravitational waves. This was a revelation. For all of human history, astronomy had been the study of light, from visible starlight to invisible radio waves and X-rays, but here was a signal from the dark. Gravitational waves are the direct messengers of gravity itself. They are created when massive objects accelerate, warping the fabric of space-time and sending those warps outward at the speed of light like ripples on a pond. Merging black holes, which emit no light at all, had finally announced their union with a silent shout felt across the cosmos. The detectors themselves are miracles of precision. LIGO and its European counterpart Virgo are not telescopes in any traditional sense. They are immense L-shaped instruments with arms 4 kilometers long. A laser beam is split and sent down each arm, bouncing off mirrors suspended in a near-perfect vacuum. A passing gravitational wave subtly stretches one arm while compressing the other, changing the distance the lasers travel by an amount 10,000 times smaller than the width of a proton. This microscopic shift causes the light waves to interfere with each other, creating the telltale chirp in the data. Since that first detection, the observatories have heard dozens more, a growing chorus of cosmic collisions. Each chirp is a unique fingerprint, revealing the masses of the objects, their spin, and their distance. We have listened to black holes of all sizes merge, and in a landmark event in 2017, we heard the different song of colliding neutron stars. That signal was accompanied by a flash of light across the electromagnetic spectrum, from gamma rays to visible light, observed by telescopes worldwide. This was the dawn of multi-messenger astronomy, where we could not only hear the crash but also see the glowing aftermath, studying the same event through sound and sight. Gravitational waves have handed us a new key to the universe. They allow us to sense the dark, heavy things that light cannot escape from, to witness the fundamental architecture of reality bending and shaking. We are no longer just stargazers, we have become listeners to the very curvature of space, tuning in to the deepest, most violent rhythms of creation. That new sense of hearing gravitational waves was joined by a sense of touch, a way to feel the universe's most violent engines with nearly massless particles that barely interact with anything at all. In September of 2017, a single, impossibly energetic neutrino struck the ice deep beneath the South Pole. It was detected by the IceCube Observatory, a colossal instrument made of a cubic kilometer of pristine Antarctic ice threaded with thousands of sensitive light detectors. This was no ordinary particle. It carried a staggering 300 tera-electronvolts of energy, millions of times more than particles produced in the largest human-made colliders. For the first time, IceCube could trace the path of such a high-energy neutrino back to a specific patch of sky with enough precision to sound an alarm to astronomers around the world. The coordinates pointed directly at a known celestial monster 4 billion light-years away, a blazar known as TXS 0506 plus 056. A blazar is one of the most ferocious objects in the cosmos, a supermassive black hole at the heart of a galaxy that is actively feeding. As matter spirals into the black hole's maw, some of it is funneled into jets of plasma and radiation that shoot out from the poles at nearly the speed of light. A blazar is simply one of these jets pointed almost directly at Earth, making it appear as an intensely bright beacon across the universe. When the alert went out, telescopes across the globe and in space swiveled to look. They saw the blazar in a state of extreme flaring, blazing with gamma rays and other high-energy light. The correlation was undeniable. That single ghostly particle and the brilliant flare of light were two different signals from the same catastrophic event. This was a landmark discovery in multi-messenger astronomy. Neutrinos are fundamental particles, often called ghost particles because they have almost no mass and no electric charge. They can pass through entire planets without ever bumping into a single atom. Trillions of them stream through your body every second, completely unnoticed. This elusive nature is also their greatest strength as cosmic messengers. Unlike light or radio waves, which can be scattered or absorbed by dust and magnetic fields, neutrinos travel in perfectly straight lines from their source, unaffected by anything in their path. They are the ultimate cosmic bullets, carrying pristine information from the heart of the violence that created them. To produce a neutrino with that much energy, protons or other atomic nuclei must be accelerated to nearly light speed and then smashed into something like photons or other matter in a process far more powerful than any supernova. The detection proved that the jet of this blazar is a natural particle accelerator of almost unimaginable power, a cosmic hadron collider on a galactic scale. For decades, scientists had theorized that such objects should produce high-energy neutrinos. That single signal from the ice was the smoking gun, the first direct evidence that these ghost particles could be used as arrows, pointing us unerringly back to the universe's most powerful particle accelerators. We are no longer just seeing or hearing the cosmos. We are beginning to feel its most energetic whispers with a sense that passes through solid rock. But these ghostly particles and gravitational ripples all emerge from a cosmos built from simpler stuff, a faint chemical haze that permeates the very space between the stars. Our final signal is not a blast or a bang, but a quiet, pervasive hum in the infrared, a set of specific wavelengths of light that glow from dusty clouds throughout our galaxy and beyond. Astronomers call them the unidentified infrared emission bands, and they are among the most common yet mysterious signatures in the Milky Way. Wherever there is interstellar dust warmed by starlight, these distinctive bands appear like a set of universal chemical notes played on a cosmic instrument. For decades, the leading explanation has pointed to a specific class of complex organic molecules known as polycyclic aromatic hydrocarbons, or PAH. Imagine the soot from a candle flame not as a messy black smear, but as beautifully structured, ring-like molecules made of carbon and hydrogen. These PAHs are thought to be abundant in space, and when they are zapped by ultraviolet light from nearby stars, they vibrate and emit infrared radiation at very specific frequencies, creating the bands we detect. They are essentially the thermal fingerprints of large organic molecules drifting between the stars. The mystery, however, is that we cannot say for certain this is the answer. While PAHs are a compelling fit, no single specific molecule from that family has been definitively identified in space to account for the exact pattern. The bands are a collective whisper from a vast, diverse population of complex carbon-based compounds, a chemical fog whose precise recipe remains unknown. This ambiguity makes the signal profoundly significant. These unidentified infrared emission bands are not a curiosity. They are a fundamental component of the interstellar medium. They tell us that the raw, complex building blocks of chemistry and potentially of life itself are not confined to planets. They are everywhere. They are manufactured in the atmospheres of dying stars, blown into space by stellar winds, and woven into the clouds where new stars and planetary systems are born. Every planet that forms does so within a nebula already seeded with these organic molecules. The signal is a quiet, universal background chorus, singing that the universe is not just made of hydrogen and helium, but is chemically rich and complex. It suggests that the path from stardust to the precursors of biology may be a common, even inevitable, process written into the fabric of the galaxy. So as we conclude our journey through 25 mysterious signals, we return not to a solitary shout, but to this diffuse, glowing haze. It is a humble reminder that some of the universe's deepest secrets are not in the catastrophic collisions or the brilliant beacons, but in the soft, persistent light of the dust itself, a signal that the cosmos is, and has always been, preparing the ingredients for what comes next. From the chemical haze of interstellar dust to the silent tremors of colliding black holes, we have wandered through a gallery of cosmic anomalies. Each signal, whether a millisecond radio scream or a centuries-long stellar dimming, is a unique dialect in the universe's hidden language. They speak of forces that warp space-time, engines that reload and fire, and structures of such delicate scale or staggering size they defy our current physics. This incredible diversity reveals one unifying truth: the cosmos is not a static museum of predictable objects. It is a dynamic, often violent, and endlessly inventive arena. The universe is far stranger than the quiet, star-strewn sky suggests. Every one of these 25 mysteries is more than a puzzle, it is an open frontier. They are the questions that force our technology to become more sensitive, our telescopes to see farther, and our theories to stretch into bold new shapes. The hunt for their answers is what propels science forward. It builds more precise detectors to catch gravitational waves and designs observatories to map the magnetic threads of the galactic center. So stay curious, keep looking up, not with the assumption that we have charted the heavens, but with the certainty that we have not. The next great signal, the one that rewrites the textbooks, could be whispering through a telescope right now, waiting for the right moment to be heard. Our story of the universe is being written in real time, and the next chapter could begin tomorrow.